Hello. Yeah. যেটা আপনার এখানে দেখে নিলে 7.3 আছে পরে আমি দেখাই Okay. Everybody here now?
class has thinned down a little bit. People are getting tired of me. Okay, now we talked about the eigenvalue assignment of a problem, of a system. Eigenvalue assignment problem, as you remember, is given a pair of matrices A, B, controllable. Find a feedback matrix F or K such that A minus B, K or Bm has a desired set of eigenvalues, right? Right. That's the standard eigenvalue assignment problem. Now, let's begin to a variation of the problem called the partial eigenvalue assignment. So, as the title suggests, we are trying to assign the eigenvalues partially, not completely. So, in the standard eigenvalue problem, we are starting from the matrix A. We don't have any idea what the eigenvalues of matrix A are. We are trying to construct a feedback matrix K such that A minus BK has all its eigenvalues, a clear set of numbers, right? It's given here. Here, suppose I have a matrix and I know the eigenvalues. Say eigenvalues are lambda 1 to lambda b plus 1 to lambda n. There are n eigenvalues. And suppose A is so large that I am not able to compute the whole spectrum. That means I am not able to compute all the eigenvalues in matrix A. Okay. But I am able to compute just few, first few eigenvalues. In practical application, these are the eigenvalues which are normally problematic. We'll talk about this a little later in context of the second order control system. Okay. But suppose the first p eigenvalues are problematic, and the remaining n minus p eigenvalues are supposed to be good, but we don't know them. We don't have any idea about them. We can compute only the first p eigenvalues. P is a number much less than n. Okay. Thus we are talking about only few eigenvalues. For example, n can be 1 million, p can be other 20, p can be 20 or 25, something like that. Okay, so we want to, what we want to do, we want to construct a feedback matrix such that the closed system will be such that those p eigenvalues will be reassigned to a given set of numbers, and the remaining n minus p eigenvalues and the corresponding eigenvectors, and the remaining n minus p eigenvalues and the corresponding eigenvectors will remain unseen. You know what I'm saying? So this problem is different from the original focus problem. So let's look at the problem again. Given that we have matrices AB, which is not controllable. Okay. And it doesn't have to be controllable. Given a pair of matrices AB, which is AB is partially controllable. Partially controllable. What does it mean? Partially controllable. That means this system is controllable with respect to those modes only, which are known. Okay. That means what I'm saying, say lambda 1 through lambda p. These are the p known nodes. So partially contributed means the rank of A minus B A minus lambda I B. Okay. I'm sorry, A minus lambda I B equal to N for I. That's what it means. If the rank would have been, if this matrix A minus lambda equal to B, the rank of each of these matrices with respect to all the nodes N, then we would have said fully controllable. Okay. In this case, we are saying partly controllable, partial controllable. So suppose so here is the statement again. Suppose that AB is partially controllable and suppose the spectrum of the matrix A is equal to lambda 1 through lambda n, of which only the first p eigenvalue lambda p are known. So the problem is construct a matrix F such that the spectrum of A minus Bn will contain the p numbers p1 through mu p chosen by you or any TS eigenvalues. And the remaining n minus p eigenvalues, lambda p plus 1 through lambda n, and the corresponding eigenvectors will remain unchanged. Okay, do you understand the problem? So, this problem is very important problem, especially in the context of large and sparse systems, for which we cannot compute all the eigenvalues. There is no way to compute the eigenvalues of a matrix whose size is, say, more than 50 hundreds. But even for this problem is meaningful even for a small system, because suppose I have a 5 by 5 system. Okay, I know only 2 modes are uncontrollable. Okay, remaining are not. So I have to change them. That's what it means. Okay, so what is I'm going to, so you have to in order to I'm actually taking this from this is not, or this is included in the book, but the proof is not included in the book. The algorithm is given the proof is not. But the proof, we have to look into a thesis based thesis of student of mine, which is available from my home page. And of course they will tell you. So here is the constructive method. So you understand the problem, right? The method is the following. So what we are going to do in having an algorithm to solve this problem, we'll only assume the knowledge of the first p eigenvalues, which need to be replaced by some other number, say mu1 through mu p, and the corresponding eigenvectors. That's all. Because we don't know anything about the n minus p eigenvalues or the eigenvectors. But we have to construct a feedback matrix in such a way that the closed loop system will be such that those first p eigenvalues is replaced by the ones given to you, mu through mu p, while n minus p eigenvalues and the corresponding eigenvectors which are not known to us will remain unchanged. So you can see the magnitude of difficulty in solving this problem. You don't know the eigenvalues, you don't know the corresponding eigenvectors, but you have to construct the closed loop system in such a way that those eigenvalues and eigenvectors will remain unchanged, and you can only work with the first p eigenvalues and the corresponding eigenvectors. That's all you have at your school. Okay. So here is a very clever algorithm. I really call it clever algorithm because you see, and I'm not able to go through the proof, but I'll tell you what the kind of proof. Okay. So so here is the here is a constructive method. Constructive method. So the first step, you compute the p eigenvalues that need to be reassigned and the corresponding left eigenvectors. Okay, not the right ones, left ones. Right. Say y1 through y2. And then from the diagonal matrix lambda 1 with those eigenvalues lambda 2 lambda, it's a diagonal matrix, and y1 is the corresponding eigenvector matrix. That means y1 through yp are the eigenvalues associated with the eigenvectors associated with the eigenvalue lambda 2 lambda. Okay, and then you compute this symbol means spectrum. Here you use the different symbol. This is the spectrum. Compute a matrix phi I mean pi. I call it phi. Right? We all call it pi, right? You know, the reason I call it phi, I have an interesting experience. I was giving once a lecture at Athens Institute of Technology in Athens, Greece. And these are Greek letters. And during my lecture, one of the young ladies like you stood up and said, "Professor, you are abusing our language." I said, "What did I do?" He said, "Professor, it's not phi, it's not pi, it's phi. It's not mu, it's me. It's not mu, it's me." I apologized to her, so I didn't know that. Yeah. But since then, I've been using an argument and now used to call it phi instead of pi. Anyway, so compute feedback matrix phi so that this will happen. We know how to do that. Given a matrix, because this is a small problem, right? We know how to do that. Lambda 1 contains the eigenvalue lambda 2 lambda p. You are going to change that to mu and to p by feedback. By constructing a feedback matrix here is called p. So this is a small problem we solve. Okay. And then step 3, we compute the matrix F that we are looking for. F is P times Y1 H. H stands for the Hermitian. Like, you know what I mean? Y1 is a set of eigenvectors. Some of them can be complex. Okay. We can avoid complex arithmetic by doing something else, but let's assume for the time being that we are using complex arithmetic. So Y1A is the Hermitian part of the Y. And if we can show that this simple algorithm is such that A minus BF, the closed loop matrix A minus BF is such that the eigenvalues lambda 1 through lambda p have been replaced by mu1 through mu p, while the n minus p eigenvalues, lambda p1 plus 1 to lambda n, and the corresponding eigenvectors did not change. Okay. It's very simple. So all we are doing, we are trying to solve a smaller feedback problem and putting them together. Okay. Well, I want to show you a different algorithm actually. It's not what I want to show you. I'll show you a different algorithm because I want to give you the flavor. Remember that we talked about computing a feedback matrix using the Aponormatic equation. Okay. To stabilize the system. And in the partial eigenvalue assignment problem, instead of using a diaphragmatic equation, we'll use a simple Sylvester's equation that will give the connection between a Sylvester's equation and the eigenvalue assignment. So let me go to that. So this is one simple way to do that. I will ask you to try both, and see how it goes. Do you understand the algorithm? What I said? The simple algorithm. So essentially, what I have done, starting from a big problem, large problem, we have been offering the solution of large problem by solving this problem. It's much smaller. Okay. Let's see. Okay. The simple solution that I could say I showed you is a method to construct just a feedback, okay, out of infinitely many, because it's a multi-input problem. If the system is partially controllable, then as in the case of ordinary eigenvalue problem, we can show if the solution exists, that means if the system is partially controllable, then there are infinitely many solutions. But the method that I give you just computes just one feedback cell, which is not desirable. Okay. We need to have a parametric solutions. That means we want to have an algorithm that will construct infinitely many solutions depending upon a parameter. That means every choice of that parameter, we will have a solution. So that solution I will show you. That solution will be as high as Sylvester's equation. Actually, those of you who are interested in this problem, I would strongly recommend you to read this thesis. This is a wonderful thesis. So, okay, so Rajiv, what I was telling you the following, that the solution that I propose here, first solution that I propose, is a solution which gives you just a feedback matrix, F, such that A minus BF will solve the partial eigenvalue problem. But the thing is that if there is a solution, it's a multi problem, there are infinitely many solutions. So we need to have a parametric representation of the solution. That for each parameter, we'll have a new solution. Okay, so I'm going to show that with the help of Sylvaster's equation. Can you help me getting to this section?
Yes.
This is
Which
5.7. This is a very interesting result that I'm going to show you now. 5.7. Yeah.
Yep.
Okay. Now the problem here, you can think of solving this problem in two parts. The first part we're going to show you is that how to preserve those n minus p eigenvalues and the corresponding eigenvectors. Okay. By doing something. How to construct a feedback matrix there so that n minus p eigenvalues and the corresponding eigenvectors will remain unchanged without knowing what they are. Okay. Now, it's very interesting to see that this part can be done as follows. And in vibration engineering literature, this is known as no spillover phenomenon. No spillover means that the eigenvalues and eigenvectors which have not been computed, which will not be reassigned, will remain unchanged. Okay. So here is the solution. Suppose I compute the feedback matrix F as follows. I say feedback matrix F is such that F equal to P times Y1H. But P is any arbitrary matrix. I don't know. I know it's a parametric, any arbitrary matrix. Then mathematically I can show that the matrix A minus Bn will be such that the n plus p eigenvalues, n minus p eigenvalues, lambda 3 plus 1 to lambda n, and the corresponding eigenvectors will not change, will remain unchanged. And the proof is very interesting. I will not be able to show you the complete proof, but what is basically will show is the following. Yeah, look into 5.11.6. So basically, we can show that if we construct our F as phi times y1 Hermitian, then that F, when you plug in here, A minus Bf x2, where x2 is the eigenvector matrix of the unknown eigenvalues. That means x2 is the eigenvector matrix corresponding to x lambda p plus 1 to lambda n. And we can show the F, if we construct F, equal to P times y Hermitian. But P is any unknown matrix. Then with that F, if we come here, we can show, this is a part of the book, we can show the following. we can show that the matrix F is such that A minus B of x2 equal to x2 lambda 2. This kind of little there are some mathematics here which I have omitted here. A minus B of fx2 equal to x2 lambda 2. Lambda 2 is the diagonal matrix of all the of the p plus 1 eigenvalues, which are not completed. That lambda p plus 1 through lambda n. Okay. Now what it means? Well, A minus B f x2 equal to x2 lambda 2. I'm able to prove that. If I prove that, what it means? It means that the, you see, that's interesting thing you have to know. A plus BF is an n by n matrix, right? So it has n eigenvalues. But x lambda 2 has n minus p eigenvalues. Okay, and x2 is the corresponding eigenvector. So this result really shows that this means it is easy, it can be shown that, okay, let me give you a simple thing result first. Suppose I have a matrix A, I have a matrix say A x equal to say x m. And I have a matrix equation like this, where A is say n by n, x is n by n, m n by m, and this is say m by m. And say m is less than or equal to m. Okay. Now, if m were equal to n and x were non-singular, then the matrices A and M would have the same eigenvalues, right? Because in that case, I could have multiplied by x inverse. So I have x inverse A, x equals to m. They would have same eigenvalues. But here, x is not non-singular, x is not square. It's n by m. But it can be shown, very interesting, it can be shown that if I given a matrix A and M, if I can construct x so that this will happen, that means that the m, that means the m eigenvalue of the matrix M will be, that means that m eigenvalue of the matrix A will be same as the m eigenvalue of the matrix M. We don't know about the n minus remaining n minus 1, but m eigenvalue is the same. And x will be the eigenvector matrix, corresponding to the m eigenvalues. It's a very interesting matrix equation result. Do you understand what I said?
Sir, again, please repeat.
Sir, is there any proof for this?
There is a proof, yeah. You can prove it. Proof into any linear algebra proof.
So please
I'll
repeat.
show you some reference.
Please repeat the set conclusion.
I have three matrices here. A is an n by n matrix. Okay. M, capital M, is an m by m matrix. M is less than or equal to n, for example. And X is a matrix n by m that satisfies this matrix equation. Oh, one thing I forgot to ask. You have to assume that X has full rank. Okay. It's a non-square matrix has full rank. Suppose this equation holds. It means, if this equation holds, it means that the m eigenvalue, you see, A has n eigenvalues, right? Suppose you partition them in the form m n minus 1 m, the two sets. The m eigenvalues of A will be the same as those of the matrix M. And the eigenvectors of those m eigenvalues are the columns of the matrix X. So exactly that is we are going to show. This happen. We can show, very interesting, we can show that by Yeah. No. Yeah, 5.8, 1.16, you can see that. So that means this actually means that our feedback matrix F has been computed in such a way that the 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 n minus p eigenvalues of A minus Pf are the same as those eigenvalues in lambda 2. That means those A minus P eigenvalues of A minus B are lambda P plus 1 through lambda n. And x2 is the eigenvector matrix corresponding to the eigenvalues. That means what I have, by constructing this feedback matrix in a special way, I've been able to show that closed loops matrix A minus Bf is such that is n minus p eigenvalues have been preserved. The original, n minus p eigenvalues of the original system have been, and the corresponding eigenvectors have been preserved. And you can look at the details of the code that is involved here. So okay, so this is the first. This is the first part of the first part of the solution of the problem. It is we call it no spillover part. So what is the remaining part? What is the other part?
So partial eigenvalue.
Right. The other part is how to assign those, how to reassign the eigenvalue lambda 1 through lambda p through mu1 through mu1 through mu p. Now the problem is a lot easier for us because p is arbitrary. So we can ask ourselves, how do we choose this matrix phi in such a way that that will happen? Okay, and there's a very clever choice of phi through Sylvester's equation. That's what I'm going to show you. Not the proof, but I'll show you how to do that. Okay, it turns out that if you choose your phi matrix by solving these algebraic linear systems, this is an algebraic linear system. Or in other words, suppose for the time being, forget about the computation. Suppose phi chosen such that phi equals some parametric matrix gamma, any parametric matrix gamma, times a matrix say Z1 inverse. Okay. What is G1? Z1 is a solution of this equation 5.1.11, which is the Sylvester's equation. And lambda 1 is the diagonal matrix with diagonal lambda through lambda p on the diagonal. Lambda CL is the diagonal matrix of the eigenvalue mu1 through mu p. And the ones that take the place of lambda through lambda p. The eigenvalue lambda through lambda p are being replaced by mu1 through mu p. And the diagonal matrix lambda 1 contains the eigenvalues lambda through lambda p, and the diagonal matrix lambda CL contains the eigenvalues mu1 through mu p. And it turns out if you solve this matrix equation, Sylvester's matrix equation, this way, choosing any arbitrary matrix gamma, okay, for G1 is solved by the G1 is obtained by solving this linear system. Okay, you don't have the actual inverse. We don't want to compute the inverse. Instead of solve a linear system. And then if you just computer, then after you get this P, then you form this feedback matrix there. Then I can show that this P which I want this, if P chosen this way, then A minus B will have eigenvalues mu1 through mu b, replacing lambda, and the problem is solved. Both the parts are done now. Why is the parametric solution now? What is the parameter here? What is the parameter here?
Parameter is the feedback.
The P has been, the choice of P has been used here. But in order to choose P, we have come up with the choice of P again in the second stage involves another parametric matrix. What is that?
C gamma G.
Gamma. The gamma is arbitrary. So this is a parametric, this gives you parametric family of solutions. Every choice of gamma will have a
Unique feed.
so we have a feedback matrix there that will solve the partial eigenvalues problem. Of course, there are some conditions to be satisfied for any gamma will not happen, and you can look at the details that gamma has to be such that that the jth component of gamma has to be equal to the complex conjugate of kth some other kth component. That means, this is how the matrix gamma has been represented. That's the
Complex conjugate.
yes. Some component has to be the complex conjugate of some other component. That's what it means. It's a small restriction, but if you do that way, follow the procedure, then the problem is solved. And interestingly, you see what we have been able to do. What is the computational burden of this problem?
Z
Well,
inverse.
You have to solve a Sylvester equation. And this Sylvester equation is almost trivial to solve. Why? Because lambda 1 and lambda CL, these are matrices here, which are diagonal matrices. I could have taken a diagonal or something else, but simplest thing is to take diagonal matrices. Okay? And we have to solve a linear system. And this linear system is a P by P linear system. Because look into all the dimensions. Lambda 1 is P by P. Okay? Lambda CL is P by P. Okay? So this is G1 is P by P. So this is a P by P algebraic linear system to solve for phi. And then you form your matrix F equal to P times Y1 Hermitian. Remember Y1? Y1 is the eigenvector matrix, left eigenvector matrix associated with the eigenvalue lambda of lambda. So all we need, the first P eigenvalues that need to be assigned, and the corresponding left eigenvectors we have done. We can then from our feedback matrix that the partial eigenvalue assignment problem is solved. So in order to solve this problem, we don't need the knowledge of n minus p eigenvalue and eigenvectors explicitly. Okay. And there's a beautiful proof of this theorem in the thesis. So look into that proof. Any question? Any question?
Sir, you talked in the before class that there is something called sensitivity of the eigenvalue. For
Yeah.
a particular eigenvalue, if you are finding the sensitivity of that particular eigenvalue, we have to find the eigenvector or left eigenvector
Right.
of that eigenvalue.
Right.
So is it something to do with this?
Yes. Well, you have a good question. Yeah, this problem. I mean, this not problem. This algorithm. The only requirement is that G1 has to be non-singular. Okay. Or otherwise, you cannot solve the system. Okay. So G1 to be non-singular. So this is Sylvester equation. When a Sylvester equation or G1 has to be well conditioned. Let's put that way. when a solution of the simplest equation, ill condition or well condition, I did not talk about that. But it can be shown the simplest result, there are a lot of results there. Simplest result is that if the matrices A and B have some eigenvalues which are close to each other, then the corresponding solution of the simplest equation will be this. So here in the situation, lambda 1 is eigenvalue of lambda through lambda p that come from the matrix A. We don't have any control there. But we have control over the eigenvalues in the lambda CL, which are mu1 through mu p. So we have to cleverly choose those eigenvalues in such a way that this situation can be avoided.
So in your chapter 10, book chapter 10, there is written that eigenvalue of A and eigenvalue of B are not same for the unique solutions.
Right.
So,
Well, yeah, that actually there is a relation that this is lambda I plus
Yes,
mu
mu
j is different from 0 for I and j. So if two eigenvalues, the eigenvalue of some, if some eigenvalues of the matrix A are very close to the eigenvalues of the matrix B, then there is a problem. But in this case, we are in a good situation. We can choose lambda CL. We know the first three eigenvalues, we can look at them and see, okay, how we choose a lambda CL. And as a matter of fact, this is the most of the engineers will have knowledge. What are the good eigenvalues to be reassigned? To be assigned. The eigenvalue lambda to lambda p, normally first p eigenvalues are problematic. We'll talk about this thing in just, in the last of the class with respect to hybridism. So last day is tomorrow, right? Tomorrow we'll talk about it. But this is a very interesting result. And this is a wonderful thesis. I'm proud of this thesis. So people, this whole thing, we started the whole thing. People didn't know how to put these things and how to. People didn't know about partial eigenvector. They always talked about eigenvector problem, old person problem. So first, first we started this. First we gave a solution, single input case, okay. And then the whole thing was generalized. The single input case, there is a paper that has been, I don't know how many times have you cited in the literature now. The paper written in 1997 with one vibration engineer and one on computer scientist from University of Adelaide in Australia. I was visiting them for a few days and this whole problem. That was the start of the whole thing. So that paper has become a fundamental paper in the area. Everybody works on the eigenvector problem as to get like that. And the most important part in that paper, which I showed here, how to maintain the no spillover. That means how to preserve those n minus p eigenvalues. But we are solving the problem in the context of second order system. There are two n eigenvalues. Only p eigenvalues have to be reassigned. So we are talking about preserving two n minus p eigenvalues and the corresponding eigenvectors. Okay. Probably we'll be talking about it in the, tomorrow sometimes. Okay, any other question? So let me go to another topic now. It's called the state estimation. Now Rajiv not here. Can we anybody else outside or he is here? So we are done for this with this topic of Dan Bank. I'll come back to that topic with the aspect of second order system tomorrow. Okay.
And today, next topic.
Is the state dismissed. So we have to go to the control. You have any tea or anything you want to break?
You want tea? Okay, I have 2 minutes.
Or you just want to break?
You want to break for some time? Maybe 5 minutes? We started late, we'll continue late.
Okay, so go to 12.2. 12.2 plus that. The two sets will be yeah. So are we taking a break or just one?
They don't want, they said no.
No. Okay, what is state estimation? Probably many of you know this problem. Remember, we start with this linear system, right? X dot t equal to x equal to y equal to c of x. Now, remember when we constructed the feedback matrix K, we don't need to know the state. It's purely algebraic. It doesn't depend upon the state x. But when you have to construct the control law E of t equal to kxt, there you need the explicit knowledge of the vector x. Also, if you have to solve this matrix equation, differential equation, you know that you need the initial value of x of t. Okay, that is needed. But it turns out that in many practical instances, you cannot have a complete knowledge of the initial state. Okay, only few components are measurable. So in that case, what you do? You need to have this state vector to implement any feedback control law. Okay. Or to find the state x of t, you need to solve the differential equation that you have been doing. There you need the knowledge of the initial state x. So the idea is now, in that case, we have to estimate the state vector x of t. Okay. And the estimate has been constructed which does not depend on any specific x0 given to you, but it will work for any x0, any arbitrary x0. Okay. And the estimate state vector, say x hat t, has to be constructed in such a way that the error between the original state and the estimated state will die in an asymptotic way. That means the error vector will approach to 0 as t approaches infinity. So then it will be good estimation of the estimate state. A good estimation of the state estimated state. Okay. You understand what I'm saying? So how do you do that? Well, there are 2-3 different ways to do that. Let me show you one way. Okay, what are the available resources we have at our disposal to solve this problem? We know the matrices A, B, and C. Okay. We know the input, we know the output. So we know the input vector E of t, we know the output vector y of t, we know the matrices agents. So using these resources, we have to construct an estimate of the state vector x of t. Okay. Now, it turns out that if you construct your estimated state vector, if you construct your estimated state vector x hat t by using this differential equation, which involves only the known resources that you have at your disposal, a minus kc, but k is of course unknown matrix. Okay, everything else is known. A is known, y of t is known, u of t is known, c is known. C is the output matrix. So it turns out that if you solve this differential equation, which is constructed out of the known resources only, then the solution of the differential equation x hat t is such that the error e of t will tends to 0 as t is persistent. That is obvious from here. Well, suppose we cannot. What is the suppose the error vector is x hat t minus x of t, right? I mean x of t minus x hat t. Okay. And so if you take the derivative, that's a function of t. If you take the derivative, you get that. So e dot t, that means the derivative of the error vector is equal to a minus kc times the error vector. And we know how to solve this differential equation, right? If of x dot t, remember if x dot t equal to ax t, then x of t is what? E to the a t x 0, right? X to the this. So same thing here. So E dot t equal to a minus kc e of t. I mean I'm saying e of t is e to the a minus kc t is 0, where e0 is the initial error vector. Okay. So the error vector et approaches 0. So how fast this error vector e of t will approach 0 will be determined by the eigenvalues of the matrix A minus K. Okay. For example, if K is constructed in such a way that A minus KC have negative real powers less than some number minus alpha, then the error will approach 0 faster in the with the rate e to the minus alpha t is 0. Okay. So the problem here is now how to construct this feedback matrix K so that A minus KC is either stable or has a set of eigenvalues, depending upon how fast you want to control the error. So again, this problem is solved by solving the feedback problem. But here, remember, we are not working with the matrices A and B, we are working with the matrices A and C. So here, the closed loop system is not A minus BF, and the closed loop system is A minus KC. Okay. So the same algorithm, and not just, you have to just take the transport, that's it. And instead of B, you have to take C. And we need the assumption, remember, we need the assumption of control bit of AB. Here we need the assumption of the observability of AC. So here is an algorithm for you. The algorithm is that given an observable pair AC, construct a matrix K so that A minus KC has a desired spectrum. Okay, you can use that any of that algorithm that we talked about, replacing A by replacing B by C. Okay, and observatory condition, the same algorithm you want. So here the algorithm will be given a observable variance C, find a matrix K such that A minus K C has a Billiard spectrum, and then you form this differential equation, solve this differential equation x hat t, then x hat t will be a good estimate of the state vector itself. Is it clear? So let's look into this algorithm. So here is the thing. So the state estimation problem using this approach is basically you have to solve the feedback problem with the pair AC and then solve the differential equation with known initial condition. Usually, so that is for any initial condition zero will work. That's the whole thing. Okay, there is another approach called, here we'll see how the problem how the feedback assignment problem or the eigenvalue assignment problem can be replaced by the problem of solving a Sylvester type of equation. And that will show you the connection between the Sylvester equation. We just saw one connection for the partial eigenvalue problem. That will show the connection between the Sylvester equation and the eigenvalue problem. This thing, what I'm going to talk about, Sylvester equation, is mathematically equivalent to the approach that I showed. It's a different way of looking at things. Okay. So let's look into that. This approach was developed by the control theorist called Weinberger, probably you have heard the name, David Weinberger from Stanford. He's still alive. He's about 95 years old. That's still alive. Yes. Yeah. Question, please. Okay. So what is this approach? How do you estimate your x of t in this case? Well, here is the theorem. So here the idea is the following. Starting from A, B, C and U, T, Y, T, which are known to us, we construct a differential equation. We construct a system with the state called Z of T in this way. Where F is an n by n matrix, G is an n by r matrix, and P is an m by m matrix, in such a way that for some constant non-singular matrix X, constant, remember that. For some constant non-singular matrix X, we do not know yet how to compute it. But the idea is that for some constant non-singular matrix X, the error vector Z of T minus X times XT, remember X, capital X matrix does not depend upon T, it's constant matrix. So we are talking about some multiple of the state. So the error vector defined in this way, G of T minus X times X of T, will approach 0 for any initial state x0, for any initial state z0, and any input and ut. So this is the idea. Okay. We'll construct the state vector and construct the estimate in such a way that, you know, here G is the estimate. So estimate in such a way that the error, which is defined as the difference between the estimated vector and x times x of t for some constant non-singular matrix x. This error will equal 0 for any initial steps. That's the idea. So now, yeah, as I said, the idea was originated by David Leuenberger and is referred in control theory as Leuenberger observer. Do you do this in your this? Yes, we do that. So they know about it. Very good. Okay. So you know about it, right? Okay. So here, remember your estimate, the state estimate is z of t, okay, which estimate a multiple of the state vector. Okay. So how to compute your matrices, that your F, G, C, V, and all those things? Well, it turns out that if you compute your matrices F, G, and C in this way, that choose your matrix F as any okay. Choose your matrix F. Look into condition number 3. Any matrix F which is stable, or if you want the eigenvalues to have certain regions of the complex plane, so choose F with some known eigenvalues. Okay. So any matrix F with some known eigenvalues, you can construct your F. So suppose F is the diagonal matrix, you can do that. Okay. And choosing that matrix F, you have to solve this equation, xa minus fx equal to gc. Now, this looks like a Sylvester's equation, but actually it's not a Sylvester's equation. It's a Sylvester's equation of a different kind. Because here, what are the unknowns and what are the knowns in this equation? F has been chosen. So what are the unknowns? Actually, you know, if you keep F as unknown also, so here what are given to you? A and C, right? And you have to find X, F, and C. But suppose I eliminate one of the constant, like F is stable matrix. Okay. Still, I have to solve that. I have to solve for X, given A, F, G, and I have to solve for X and G, given A, F, and C. And there is a way to do that. Because G is a very especially, G is not a full matrix. It has some special structure. This can be done. And so, since it's not really a Sylvester equation, a Sylvester-like equation, I call it Sylvester's observer equation. Okay. And this is the terminology I introduced in the literature. So, people are using the term Sylvester's observer equation, because Sylvester's equation, a very special type of Sylvester's equation arising in the design of observer. So you solve this equation, and from there you construct the matrix P, which is X times P, and then we can show the following. Then remember this differential equation you have to solve. You know, once your F, G, and the matrix P matrix is constructed out of the solution X of the Sylvester equation, Sylvester objective equation, right? And once the P matrix is constructed, D is known, F is known, then you have to solve this differential equation for any initial C0. You can choose any arbitrary initial C0, you solve it. Okay. Then we are able to solve, that's what the Leuenberger proved, that the error vector E of t, which is the difference from the new estimate vector G of t minus x times some multiple of the original state vector weighed up to 0 for any choice of x0, g0, and ut. Okay, that is the theorem. So the whole thing is how to compute that, and how to construct the solution of the Sylvester's observable equation. Okay. If you can choose as a diagonal matrix or a triangular matrix with known a stable or known eigenvalues. So problem is how to choose the matrix X such that XA minus FX is. And there is an algorithm like the Heisenberg algorithm that we do now. Heisenberg, remember how to solve the simplest equation by Heisenberg-Schur algorithm. Remember, one of the matrices was transformed into Heisenberg, other one in Schur. So here also there is an algorithm like that. One of the it's not it's a very clever algorithm due to Paul van Doren, and you can look at the algorithm in the book to construct that thing. Okay. There's a way to construct. Based on the algorithm. You have to, of course, instead of first of all, instead of putting into the controller Heisenberg form, you have to put into the observer Heisenberg form, because you have test the observability of the PRAs. Okay. First of all, you have to remember the system has to be observable, otherwise you cannot estimate the state. The system needs to be observed. It has to be observable. That means the matrix AC has to have full rank. Okay, not AC. Yeah. AC has to be observable pair. That means the observable matrix C, CA up to CA to the n minus 1 has to have full rank. And you can have the Heisenberg, observer Heisenberg form to do that. And actually the algorithm for solving that simplest object equation is based on reduction of the pair AC to observer Heisenberg form, not control Heisenberg form, observer Heisenberg form. But here is a simple algorithm that's to show you how to work. So with this choice of G and F, and we solve this equation X by using that. When G and F is known, then it's an ordinary simplest equation. Okay. The trick is how to choose G. Okay. So the G has to be cleverly chosen. So you can so that you can solve this equation, get your X, and construct your P, and then you remember you have to construct your Z of t by solving this differential equation for any arbitrary initial condition Z0. Once G of t is computed, then X hat t is X inverse Z of t. That's your estimate statement. And there is some you can see that from the small example that I showed you here. we estimate the state by using the algorithm, the Sylvester's object, by solving the Sylvester object equation. And you can see how, this is the second variable, this is third. There are three components. So the first and second variable, this is the first variable, how, and the solid line represents the state, and the broken line is estimate. And so second and component of x is estimated very accurately. So, okay. So let me now talk a little bit about how to solve that Sylvester object equation. We have time to do that. Well, there is a version of these things which I am not going to talk about. It's called reduced order observer. Reduced order observer means, because as I said, that some states may be known. So you don't want to compute the whole states. You want to compute only the states which are not known. So then the problem size becomes reduced. Then. Instead of solving for n by n matrix, now you are solving n minus r matrix. So the matrix equation that involves solving the matrix X will be of order n minus r, where r states are already known. Okay. That reduces some burden, and then you way to do that. You can look into that theorem. I'll do it. So here is a comparison, I think, comparison between the two approaches. One is the feedback design approach, another is Sylvester equation approach, right? And but the same problem is, I think it's a different problem. So this is for the reduced order observer. Sorry, this is not the computer observer. But you can do your own example to compare the two approaches. Okay. The feedback approach is simple. Okay. Because you just given a observer by SC, you just compute a feedback matrix K, so A minus KC and the digit set of eigenvalues. Once you do that, then you solve the differential equation. You have done. Here you have to, of course, you have to solve the main computational burden here. How to solve Sylvester object equation. Okay, that is a nice algorithm to do that. I'll show you that. Any questions so far? Okay, yeah, let's look into this clever algorithm for solving the Sylvester object equation. As I said, it's based on the reduction of the pair AC to control to observer deliver. Okay. So what we are doing here, we are transforming the matrix A to an unreduced block upper Heisenberg matrix. So you have to take a break for 5 minutes.
Just 5 minutes.
Se saca el
controller Heisenberg form. Only thing, you have to replace the matrix B by the matrix C. Same algorithm. You can look at the book. So by doing that, what you get, you transform the matrix A to an unreduced block upper Heisenberg matrix. That means the block upper Heisenberg matrix with all the subdiagonal blocks have been pulled out. And at the same time, your C times O transpose, the O is the transforming matrix, has a special form, where C1 has full rank. In case of Heisenberg controller form, you have B1, 0. Here is G0, C1. Okay. So, if using this transformation, now Xa minus Fx equal to Gc is then transformed to this matrix equation. YH minus Fy equal to Gc prime, where Y is nothing but X times O transpose. It's a simple, I've shown you this calculation. Okay. So now the problem is solve this equation, this reduced equation. YH minus Fy equal to Gc prime for Y. Given H, the block unreduced upper block unreduced block Heisenberg matrix. And choosing, of course, you have the activity there. And once you compute Y, then you can compute X as X equal to Y O, because O is an orthogonal matrix. Okay, that's it. So now the problem is how to solve this reduced equation, taking advantage of the special structure of the matrix H. Okay. So there's a nice algorithm to do that. So instead of doing that, what I'm doing, this is a recursive algorithm. Very nice algorithm, very old algorithm. Here, what has happened, Y has been assumed in the special form. That means it is assumed that Y, the diagonal blocks of Y are all known to be equal to 1, and you have to compute the off-diagonal blocks of Y. Okay, I mean off-diagonal entities of the matrix Y. The matrix M, remember, has to be stable or has to be a matrix with known eigenvalues. Okay, so we take the matrix M in this case, it's triangular matrix. Okay. In this special form, where because of the computational convenience, we are taking these matrices in this special form, and there is no harm in doing that. So F is a lower triangular matrix with the diagonal entries to be known, because F has to be a matrix with eigenvalues are not here. Okay. In particular, if you want the F to be stable, you can choose the entries F11, F22 up to Fq as some negative numbers. That's it. So then you have to, the off-diagonal entries of F have to be computed. And G is taken in the special form. This is Q, not 9. It looks like 9 is not 9 is Q. Okay. So the algorithm is now compute the matrix Y in the special form, choosing F and G in this way. And the best thing to do, it can be done recursive. Okay. The entries of Y, the entries of unknown entries of the matrix Y, the unknown entries of the matrix A, and the unknown entries of the matrix Z can be computed simultaneously in a recursive fashion. So let me illustrate the whole idea with the help of a small algorithm that will give you a sense of how to do that. Okay, then you can look into the general algorithm. You know what I mean, right? So let's look into that simple example. Okay. Well, let's look at special case. N equal to 3, R equal to 1. Okay. Even R is remember what is R? Is
QR.
the R. The R is what? Small r is what? Dimension. What is the dimension of the C matrix?
N cross R. N cross R.
R. So R is here in this case 1. Okay. Okay. So suppose we have this case. So I take the special case where N equal to 3, R equal to 1. So we have to solve this equation. Okay. So Y is here 2 by 3 matrix. Diagonal entries are all known. 1, 1. So you have to compute Y12, Y13, and Y23. Each, of course, is completely known. F matrix, F1 and F22 are known. You have to compute F21. Okay. And G matrix, C1 of this is not real. The G matrix, you have to compute G1 and G2, 2 entries. And you can see it can be done recursively. Okay. You can compute several entries at a time. Yeah. So if you compare the first row of the last equation, then no, it's first row of the first equation, not last. It's a mistake. First row of the first equation, then what do you get? You get this equation: y12 h21 equal to f1 minus h1. 1. Remember, everything here is known except y12, right? So y12 we can compute here. Just divide by h21. f1 is known to you. So you can compute y12 from the equation number 1. Once y12 is computed, you can compute y13. y12 is computed, y13 you can compute from the second equation. So we are computing y row by row. Okay. And once y12 and y13 is computed, then you can compute g11 from the third equation. Okay. If y13 is known, y12 is known, you can compute g11. Okay. So at the end of this step, you have been able to compute y12, y13, what else?
G1.
y12, y13, and g11. 3 entries you have to compute. We still have to compute y23. Okay. We have to compute f21 and g21. Let's do that. We can do that in the second step. Yeah. Now we compare the second row, entries of the second row. Then you can see your f21. You first compute your f21, and then once f21 is computed, then in this stage you can compute y23. So f is completely computed, f is completely computed. So the remaining entry of g is computed from 30%. Everything is computed. So you see, if you understand what is going on here, you are exploiting the special structures of the matrices Y, F, and D. Y has been taken in a special way. So it's an upper triangular matrix with ones along the main diagonal. Of course, it's a non-square matrix. F has been taken in such a way that it is an upper triangular matrix of lower triangular fiber with the diagonal entries known. And G is like this. So by equating the entries row by row, you can compute all this very easily. And this idea is carried out in the same idea is implemented in the general case. So you can see how easy the algorithm is. And once you compute Y, then you compute X. and then you just plug in the algorithm. That's it. Do you understand? So let's look into an example. So here is an example. N is 4, R is 2. First, this is your observer Heisenberg pair. That means observer Heisenberg form is H is in this way. Do you see why it is? H is a unreduced block Heisenberg. Where there are two blocks here, and this is diagonal block, one diagonal block. And C prime is this way. And your O matrix is a very simple matrix in this case. It turns out to be a simple matrix. And as I said, that the diagonal entries of F have to be chosen, can be chosen arbitrarily, depending upon whether you want to assign certain set of eigenvalues or you want the matrix F to be stable. Right? So you choose F1 equal -1, -2. So you have to stabilize the system. And you solve, then you get your Y1 and so on and so forth, then you get the solution. And this is your F, this is your G, this is your Y, from your X, and you can check that this X what you computed by using this recursive algorithm, or you use the recursive algorithm to compute Y and then multiply by the orthogonal matrix O, which comes from the observer Heisenberg form. Okay, and then get your X. It turns out, so you can check how good the solution is, and it's so that the two norm X minus Fx equal to GC, that should be 0, right? So this should be 0. The two norm is the order 10 to 14. Okay, so it's quite good. And this algorithm, actually, this algorithm has been proved to be stable algorithm. And good thing for you that math control has a function called SILV OBSM, Sylvester Observer Equation. Okay, you can use that. Okay, I'll stop here for now. In the afternoon, we'll be doing something else. Okay.
Okay, Professor, I will put forward few questions.
Sure.
You can just take your seat.
You are going to ask me some questions.
Yeah. So you can take your seat, you can listen then.
My
What
God.
are our concerns? Yeah, you can take your seat.
That's okay.
First, from the perspective of control engineer, few things which are hovering in our mind at this stage is that there is a striking two computational techniques that you have been talking about is a Lyapunov equation and Sylvester's equation. We know that how to fit Lyapunov into control theory.
You know, in the element setting.
No element. Okay, so
What do you mean? You know how,
uncontrolled setting.
what does it mean?
Yeah, I'm telling you. So we control engineers. We always start with a problem where there is a dynamics given.
Yes.
That's what is always in our mind.
Yeah.
Whenever we talk of a control problem, we know that this is the system that is given.
Yeah.
And then we know that what are the problems that we solve given these dynamics. First problem we deal is to test the stability.
Yeah.
That we are concerned about.
Yeah.
Second, we talk about the control.
Yeah.
Or stabilizability.
Yeah.
Of course, connected with it may be the performance.
Yeah.
Okay. Or optimal control.
Yeah. So we did everything here.
Right? So we know, or say observer designs.
Yeah.
Observer-based control, output feedback control, state feedback control. Right? So we know how to move to Lyapunov equations through the connection of Lyapunov philosophy to arrive at Lyapunov equation, and then the question comes about using your techniques. That is the solution. Right? Question is, how do we move to Sylvester's equation given this dynamics? Suppose I am designing an output feedback control problem. I can do it using Lyapunov because I know the Lyapunov's first theory or the second theory to come up to the limit. But how do I come to the Sylvester's equation starting from these dynamics?
Well, the Sylvester's equation, all you need to know A, and then depending what problem you want to solve, the Sylvester's equation will differ. The only thing we are using Sylvester's equation here is to solve the partial polar solution problem, partial eigenvalue problem, and determining observers. That's all.
Say if we try to talk about the stability of a system
Yeah.
and we want to use a Sylvester's equation, is
No.
it possible?
No, because we are going to use the
In that case,
stability of theorem. Stability is associated with one single matrix here.
okay,
So it's Lyapunov.
But-
So Lyapunov equation is a special case of Sylvester's equation. You see, X plus Bx equal to C, but B equal to A transpose, it becomes Lyapunov matrix equation.
okay. Now for stability, if from stability we want to go stabilizability,
Okay.
right? So
Yeah,
using
yeah, I-
Lyapunov, we can directly extend
So
Lyapunov.
there I showed you Lyapunov matrix equation approach.
Yeah.
Which is not good approach.
Because
Which gives you
higher value substrate.
the matrix K
Yes, much more.
can be arbitrarily large with Lyapunov matrix.
Okay. Fine, the question is understood.
Yeah.
Okay, the solution is understood. My question is how to arrive. I hope I can make you understand how to arrive at Sylvester's equation.
Why do you need Sylvester's equation there?
Say if I am trying to control, I want to have a stabilizability.
Yeah.
Stabilizability problem.
Yeah.
Right. So in Lyapunov, I have one advantage while formulating the solution is from stability I can move on to stability. I can have two things together.
Mhm.
Whatever condition of stability I propose, I extend simply under closed loop for stabilizing. So how do we do it in the formula while formulating or going by Sylvester's?
Why do you need to go? Because Sylvester's equation is general equation. If you can do it with the help of Lyapunov, why do you have to think of a Sylvester? Sylvester has to think when you are talking about when you are working through a set of matrices, a pair of matrices. Okay. Here you are not talking working with a pair of matrices. You have stabilizability problem, given a matrix A, okay, and given A and B. Okay. You find a matrix A, so the A minus B is stabilized. So
So we start from this particular notion.
yeah. So there is no need for invoking Lyapunov Sylvester's equation there. But that's some cases you need to solve this Sylvester's equation. So those cases that we talked about. Okay, you see Lyapunov matrix equation again. Like you can test the controllability of system, controllability of a stable system using Lyapunov matrix equation. You know that. You know, x plus a plus x minus b beta. When A is stable, if you can come up with a symmetric definite solution, then. But the Lyapunov Sylvester's equation is not needed. So Sylvester's equation has been conveniently exploited only in the few design problems, not every.
More from the computational aspect.
Or from computational aspect also, you see for example, the technique that was showed to solve the partial polarization problem. I cannot do it to Lyapunov.
Yes, where we want to
Because there are two matrices we are working with.
which
One
is
is a matrix, a diagonal matrix of the given eigenvalues, and one the diagonal matrix of the eigenvalues to be assigned.
assigned.
So there, I don't have any choice other than working with the Sylvester's equation rather than a Lyapunov matrix. Okay. If you want to reassign the same eigenvalues, which I don't want to, that is a stupid thing to do, then I can, of course, I can use this the left robotic equation is also useless. So simplest equation is a good tool, but we don't have to use every time. We will use it when it's needed. Otherwise, we can do everything with left robotic equation. That's the idea.
Thank you, thank you. And I think as you have already talked about state feedback and code placement, if time permits, we would like to hear from you output feedback.
I don't think we have time to do that. Not much is known about output feedback anyway.
Little bit we want to know because there are complexities in output feedback.
Yeah, but it's not much known about that.
Though we have solutions by observer-based state feedback, but still it is better if we can learn little bit from you on output feedback because there, there are some restrictions on symmetry.
There are not very work, that not, the output feedback only very little.
But I could find something that is there in your book. On
Yeah,
output
or
feedback.
there is something, but there is an algorithm there. The algorithm is too complicated to implement.
Just an idea, so that at least because there are some complexities in output feedback compared to state feedback,
Of
but
course,
this is
yeah.
practically more useful for us because in many situations even we cannot construct state feedback. We can construct, but if I have only one measurable state and I can measure that state very easily, and if I can construct output feedback, right, it is saving of time. But computationally, how difficult it is, at least if we have an idea, and if we listen from you, that will be nice on output feedback. And second, the house is really interested to know more about H infinity control, little bit, and to augment H infinity control, this knowledge, and little bit if you talk about minimal realization of transfer function.
Okay.
So I think here we will
Okay,
finish, and
we are in the second half today.
Okay.
I'm going to talk about Kalman filtering
Okay.
and the
LQG.
Yeah,
Okay.
that will take the whole thing.
Okay.
So we are left only lectures
4 hours
4 hours tomorrow.
tomorrow.
So we want to talk about the vibration control. Right?
Yes.
Second order control.
Yes.
Some of the students are interested.
Yeah.
So I need about 2 hours to do that, and another 2 hours I can see what I can.
Yeah. So these are something
Yeah, I'll
I
see
just
how-
projected.
Yeah, I'll have to do it. I'll class these topics very briefly.
Yes, very good.
I won't have time. To
Yeah.
do it.
So I think if they understand little bit about this, then going to H infinity will be easy.
Okay.
That it was. Thank you. So we meet at 4 o'clock today.
Yeah.